All right, so I just made a video, it was about a half an hour video going over the different solutions to the integrals worksheet, and unfortunately I just found out that the sound was off. Classic math professor goof up. So what I wanted to do is just take a few minutes and walk you through each of the solutions. I have all the problems written out, and I just wanted to show you how they all went. And then I'll upload this PDF as well. So I'll upload the actual work so that you can see all the different solutions. So for the first integral, we just expand x plus 1 squared, group all the terms, and plug everything in. It's pretty straightforward. For the second integral, what we did was we substituted u as cosine theta. That made du minus sine theta d theta, and then we changed the bounds, and we ended up with e minus square root of e minus e to the 1/2. For the third problem, we did partial fractions. So the integral of 1/2t squared plus 3t plus 1. We did a partial fraction decomposition, and then that integrated like that. Notice that the 2 here, so there should be a 2 outside, but then also you get a 1/2 from integrating 1/2t plus 1. So those cancel out. You get natural log of the absolute value of 2t plus 1 minus the natural log of the absolute value of t plus 1. For part D, what we did is we took one of the sine thetas and split it off and wrote sine squared theta is 1 minus cosine squared theta. And then we substituted u as cosine theta. Okay, and we ended up getting 2/15. Part E was super straightforward. U is natural log of t, and this became the integral of sine of t, so that's, I just realized that should be a minus. Let's think about this. Yeah, minus cosine of natural log of t. I think that should be a minus. Let me think about that for just a second. Yeah, minus cosine natural log of t. For part F, we did a trig substitution, so we let x be secant theta, and then dx is secant theta tangent theta d theta, and this turned the integral into, we changed the bounds as well. So when x is 1, then secant theta being 1 means that theta is 0, and when x is 2, secant theta being 2 means that cosine is 1/2, so theta is pi/3. And so this turns into the integral from 0 to pi/3 of tangent squared theta after you cancel everything out and balance everything. And then we write tangent squared as secant squared minus 1. We can integrate all that, and we get square root of 3 minus pi/3. Part G was a little tricky. We talked about this in class, but we're going to let u be cube root of x, and then we're going to solve for x, and then that'll let us find dx a little easier. So it turned out dx was 3u squared du, and then if we plug everything back in, this is an integration by parts where we had to do it twice. So the integral of u squared du we found over here. So that was letting f prime be e to the u and letting g be u squared. That means f was e to the u, g prime was 2u. So that's a u. And then we get f times g minus the integral of g prime times f. And then finally we had to do integration by parts again. So the integral of u e to the u, we did integration by parts again. And we ended up with u minus 1 times e to the u. And so when we put everything together, we put u minus 1 times e to the u here. And then we put, that makes this, so yeah, just putting this all together, maybe I did it here. So the integral of u squared e to the u was what we found it to be. It was u squared e to the u minus 2 times this integral. And so altogether that was u squared minus 2u minus 1. And so we put that here, substitute back in, u is x to the 1/3. And so u squared is x to the 2/3, and so on. And substitute everything back in, and that was part G. Okay, so the trick here, let u be the cube root of x, solve for x, and then that lets you find dx a little easier. H is a classic integration by parts, so we split it up. We do the not integration by parts, it's classic partial fraction decomposition, that's what I mean. We do the partial fraction decomposition, we get a is -1/2, b is 3/2. And then we can integrate that straight away. For part I, we took the square root of x and wrote that as x to the 1/2 and brought the 1/2 out. Okay, so that's where this 1/2 came from. And so now we can do integration by parts. We're going to let f prime be x to the 4th. We're going to let g be natural log of x. So this is the thing that we want to differentiate. And that makes the other part what we want to integrate. And so even though the power of x is getting bigger, we change the natural log to a power of x, which makes things nicer. And then when we plug in, this is what we get. So we get 1/10 x to the 5th natural log of x minus 1/50th x to the 5th plus c. For part j, we don't need to do anything really. We just split it. And then we use the fact that we know this integral of 1 over x squared plus a squared is 1 over a inverse tangent of x over a. And so this first bit, you can write 2 and then 1/2 if you want to do it that way. Anyways, that's the first integral is a u substitution if you want to do that. For part k, what I did is I did a trig substitution, but all in one step. So we let x minus 3 be 3 secant theta, because this is something squared minus 9. So that's 3 secant theta. And then dx is 3 secant theta tangent theta d theta. And then, yeah, so our dx is 3 secant theta tangent theta d theta. Our x minus 3 is 3 secant theta, so that squared is 9 secant squared. And then what ended up happening is we had a square root of 9, so factor out the 9. That leaves us with secant squared minus 1, which is tangent squared. Take a square root, and that cancels with tangent. The square root of 9 cancels with the 3, and we're just left with secant theta. And so when we integrate secant theta, we get 1/2 natural log absolute value of secant theta plus tangent theta, and then we can plug back in with a triangle. Okay, with the triangle, what we did is secant theta is x minus 3 over 3, so cosine is 3 over x minus 3, and then when you plug everything back in, this is what you get. Notice that you always seem to get in your triangle part of the integral. Okay, so the thing that's in the integrand always appears somewhere, or some part of the integrand always appears somewhere in the triangle. So that was part K. Part L, oh, and I'm sorry, the last thing for part K, notice that here you can take this and write this as the natural log of the numerator minus the natural log of the denominator, which is a constant, and then you can absorb that into that constant c. So that's why you can get rid of the denominator there. Part L it looks like just a trig substitution, so x is tangent theta. We end up with, when we follow everything through, we end up with the integral of cosecant theta d theta. And so that's going to be negative natural log absolute value cosecant theta plus cotangent theta plus c. Use the triangle to write everything in terms of x again. Part M, here we take sine of 2x and wrote it as 2 sine x cosine x, and substituted u equals cosine x. And then follow everything through, we get 2/5. For part N and part O, I think these problems are slightly too difficult for the exam, but if you follow them, that's a good indication that you are doing great with this. Okay, and so these are still problems that should be wrestled with a little bit. I think having these problems cold on the exam is a little bit much, but yeah, anyway, so here I think the easiest way is to let u be the square root of e to the x minus 1. And the reason why I want to do that is, well, we can do the usual trick and square it and kind of solve for x. We don't really need to solve for x completely, because if we stop at e to the x minus 1, when we take the differentials, we get e to the x dx, and we have an e to the x dx. So that's why we can stop there, and then that gives us 2u du. And so let's just think about how everything balances. We do have to change the bounds. When x is 0, we get e to the 0, which is 1 minus 1, so u is 0. And when x is natural log of 10, we get e to the natural log of 10 is 10. 10 minus 1 is 9, and then square root of 9 is 3. Okay, so our bounds go from 0 to 3. And then let's just look at how everything balances out. Okay, so I think the actual substitution part is the trickiest. So our e to the x dx became 2u du. Square root of e to the x minus 1 was our u, so that's our u there. And then e to the x plus 8, if we take e to the x minus 1 and add 9 to both sides, we get the e to the x plus 8 is u squared plus 9. And then we have u squared over u squared plus 9, where we can add 9 and subtract 9, so it's adding 0, and split it up that way. Okay, and so this is basically like when we did partial fractions and we had a degree of the numerator being the same or higher than the degree of the denominator, we had to do division. This is what you would have gotten from the division. You can just do it very quickly with one algebra step. And so this turns out to be the integral of u minus, if I bring out the 9, this is again the 1 over u squared plus a squared. So 1/3 inverse tangent u over 3. And then when I multiply by 9, I actually get 3. And so when we plug in u equals 3, we're going to get 3 minus 3 inverse tangent of 3 over 3, which is 1. Okay? And then when we plug in 0, we get 0. And so this is 6 minus 6 pi over 4. Finally, for part O, we have inverse sine of x over x squared. So here we did integration by parts. The idea with integration by parts is that this maybe would let us get a handle on the inverse sine part. So if we differentiate that, that means that we would have to integrate the 1 over x squared. So our f prime is 1 over x squared. That makes our f negative 1 over x. Our g is inverse sine, so the g prime is 1 over square root of 1 minus x squared. And then plug everything in, and then we get this integral. And the way that I had originally thought to do this integral was with a clever substitution, which I'll show you in a second. But it turned out, and I tried this kind of on the spot at the time, that a trig substitution is much, much nicer. And so if we let x be sine theta, dx is cosine theta, this becomes the integral of, after you plug everything in and follow through, this becomes the integral of cosecant theta. And so that's negative natural log absolute value cosecant theta plus cotangent theta plus c. And so this is negative natural log 1 over x plus square root of 1 minus x squared over x. Okay, and that's a straightforward way to do that integral, so you can put that there and get a plus c. The other way that I thought to do this was to take the integral. So this is our integral that we started with was 1 over x times square root of 1 minus x squared. And then I multiplied by, so we would let u be the square root of 1 minus x squared. And then we can square both sides. So u squared is 1 minus x squared. And then we can, I guess we want to still do the du over here. So our du would be negative x over square root of 1 minus x squared. And so we have a 1 over x squared, 1 over square root of 1 over the square root of 1 minus x squared in our integrand dx. We don't have a minus x, so what we can do is we can put a minus x there at the cost of kind of balancing everything. So we have to put another x in the bottom, we have to put a negative out front, and then this will give us negative integral 1 over 1 minus u squared, and that's either the integral of arc hyperbolic tangent, or you can do a partial fraction decomposition. Okay, it turns out that arc tangent is equal to something like this. So it turns out that arctang, so inverse hyperbolic tangent of x is equal to 1/2 natural log 1 minus x minus 1/2 natural log absolute value 1 plus x. Okay, so it turns out that that's true for all x. Any way you want to do it, you end up with this kind of ugly looking integral, which is similar but not quite exactly what we got up here. Okay, and so if you rationalize the denominator, you'll see that those are the same, but that's the worksheet in a nutshell. Okay, so again, the idea is I wanted to do this in a video so that you can have something to refer back to, and we're not going to spend any more class time with this worksheet. Okay, go over, make sure that you know how to do every single integral on this worksheet. I don't think that there's any integrals here that are, with the exception of the last two. So I know I said that n and o are a little bit too hard for the exam. I think with those exceptions, the rest of them are completely fair integrals that you could see on the second exam. Okay, so you should be able to know how to do all of those integrals, all of those types of integrals. Okay, and as always, if you have questions, just let me know.